We present a multi-class hinge loss for training conditional GANs. Our multi-hinge generative adversarial network, MHGAN, incorporates class information into the state-of-the-art GAN hinge loss via a multi-hinge generalization with an auxiliary classifier. This improves the fidelity and diversity of generated images. We also demonstrate the importance of not sharing parameters between the tasks of discrimination and classification with MHGAN, where we use our loss to make projection discriminator embeddings better for classification. This results in increased fidelity but decreased diversity of generated images. GANs are a training strategy to create a generator G which takes as input noise Z and outputs data like images X. The generator is trained with a discriminator D that makes a decision capital D if X is real or fake. The discriminator is trained so that its decision matches the underlying true hypothesis H, while the generator is trained so that the decision does not match the truth. Current state-of-the-art GANs like self-attention GAN or big GAN use the SVM-like hinge loss with a projection discriminator Wasserstein GAN. This network uses class information Y via an embedding inside the network architecture when making the real-fake decision. The discriminator learns an affinity, not probability, of positive value for real images and negative value for fake images. A margin of size 1 is enforced around the decision. When training the discriminator on real images, an affinity greater than +1 results in no training gradient, and for fake images an affinity less than -1 results in no training gradient. However, despite this being a conditional GAN, the generator is not trained to explicitly respect its conditioning, and the discriminator is not trained to have a higher affinity for the correct class. One would expect if a discriminator receives an image of a fake bird, making a decision whether this is a real truck should have less uncertainty than the decision of a real bird. We propose to use this multi-class hinge quantity that enforces a margin of size 1 between conditioning on the correct class and all other incorrect classes. When training the generator, this quantity has the following effect. Suppose we have begun training a discriminator on 3 classes with the real data shown as solid points. The decision boundaries are in black, and the decision classifications are shaded. Then, we generate samples, hollow points, from our generator, with their color showing their class conditioning. Fake green samples are incorrectly classified, so the generator is updated according to the classification boundary to make more realistic samples. Blue fake samples are correctly classified, but within the margin of uncertainty, so the generator is updated to make more realistic samples again. Red fake samples are correctly classified with certainty, so the generator is not updated in this case. We use this multi-hinge loss to train a network with an auxiliary classifier. We compare to the projection discriminator baseline and cross-entropy as AC-GAN introduced to train the classifier, and find that our MHGAN performs best on ImageNet 128, with some samples shown here. Our MHGAN only requires 1 discriminator step per generator step to train successfully, unlike AC-GAN. In addition to improving IS and FID, MHGAN improves the diversity of samples as measured by intra-FID. We discover by using the same multi-hinge loss but also sharing parameters between the projection discriminator and the classification task that we can improve IS and FID greatly and quickly at the cost of generator diversity. By taking a halfway trained self-attention GAN, after just 5,000 more steps, the IS rises to an incredible 169, and the FID improves to 8.8. By looking at the before and after pictures, however, we see a drop in diversity in samples. Yet, this can yield a high fidelity generator at the fraction of the training required by other ImageNet GANs. In summary, we incorporated an auxiliary classifier fully compatible with Wasserstein-based GANs that improves and speeds training, unlike cross-entropy solutions. We showed that sharing parameters between classification and discrimination tasks with this